The calculations for a paired test for two population means. To complete the calculations for a t-test to compare two paired population means, we assume that we have two measurements from each of the n elements of the population. For example, element A has two measurements called A1 and A2. Element B has two measurements, B1 and B2. Then C1 and C2, D1 and D2, etc. for each element. The null hypothesis is that mu1, the population mean of the first set of measurements, is equal to mu2, the mean of the second set of measurements. The easiest way to think about the calculations is to note that since the observations are paired, we can think about the difference between the two measurements as the variable of interest. For example, for element A, we take the difference of the measurements A1 minus A2. For element B, we take B1 minus B2, then C1 minus C2, then D1 minus D2, etc. for each element. So another way to think about this hypothesis test is that the null hypothesis claims the population mean of the differences, often referred to as mu d, is equal to 0. When we consider this formulation of the problem, we see that this test is just a test for one population mean, where the mean happens to be a mean of the difference between two other measurements. So this test is done as any other hypothesis test for one population mean, using a t-statistic with n-1 degrees of freedom and a test statistic t equals x bar minus mu0 divided by s over the square root of n, where mu is some proposed value. Here the sample mean is the mean of the sample differences, normally called d bar, and we use that in place of x bar. For example, if our sample data consisted of 4 observations, observation A has measurements 5 and 2, so the difference d is 3. Observation B has measurements 11 and 5, so the difference is 6. C has measurements 10 and 8, so the difference is 2, and observation D has measurements 13 and 6, so the difference is 7. Then the sample mean difference, D bar, is 3 plus 6 plus 2 plus 7 divided by 4. This turns out to be 4.5. The sample standard deviation of these differences is referred to as S sub d and is simply the sample standard deviation of the variable representing the differences. This can be calculated using statistical software or Excel using the equals stdev.s function. Alternatively, it could be calculated by hand using the formula for standard deviation. Using the numbers from our earlier example, we would get S sub d equals 2.3805. Usually, but not always, we want to test the null hypothesis that the population mean difference, mu d, is equal to 0. In this case, our test statistic would be t equals x bar minus mu 0, here d bar minus 0, divided by s over the square root of n, here sd over the square root of n. This has a t-distribution with n-1 degrees of freedom. In our example, we have d bar equals 4.5, s sub d equals 2.3805, and n equals 4. So our test statistic t equals 4.5 minus 0 divided by 2.3805 over the square root of 4. This turns out to be about 3.78. To determine if the null should be rejected, we can use either a critical value or a p-value approach. For a critical value approach and the level of significance alpha, we want the values on a t-distribution with n-1 degrees of freedom that cut off alpha percent of the probability to the outside of those critical values. We reject if our test statistic is outside these values, which can be found by using a t-calculator or a t-table. In our example, if we use a 5% significance level, we had a t with 4 minus 1 or 3 degrees of freedom, so the critical values are minus 3.181 and positive 3.181. In this case, the test statistic was t equals 3.78, so we reject the null that says that the mean difference is 0. In other words, we have evidence that mu1 does not equal mu2. Alternatively, we could use a p-value approach. For a two-tailed test, the p-value is the probability that the distribution is outside the test statistic t and it's negative, and we reject the null if the p-value is less than alpha. In our example, t equals 3.78 and the sample size was 4, so we use a t with 3 degrees of freedom. Using a t calculator or a t-table, we find the p-value is about 0.0324. Because the p-value is less than alpha equals 5%, we reject the null that the mean difference is 0 and have found evidence that the two population means are not equal. Now, in some cases, we might want to try to do a one-tailed hypothesis test. For example, suppose that we want to find evidence to show mu1 is greater than mu2. Then the null hypothesis is that mu1 is less than or equal to mu2, or in other words, that mu d is less than or equal to 0, And the alternative is that mu1 is greater than mu2 or that mu-d is greater than 0. We can use a one-tailed critical value or one-tailed p-value to conduct the test. Using a critical value approach, we reject the null if the test statistic is greater than the critical value, cutting off alpha percent of the probability to the right on a t with n-1 degrees of freedom. In our example, n is 4, we use a t distribution with 3 degrees of freedom. So for a 5% significance level, we reject the null if our test statistic is greater than 2.35 for the critical value. Since t equals 3.78, we do reject and conclude there is evidence that mu1 is greater than mu2. If instead we use a p-value approach for this one-tailed test, the p-value is the area to the right of the value of the test statistic on a t with n-1 degrees of freedom, and we reject the null if the p-value is less than alpha. In our example, for 3 degrees of freedom and a test statistic of 3.78, the right-tailed p-value is 0.0162, and so if alpha is 5%, we reject the null and conclude there is evidence to suggest mu1 is greater than mu2. For a one-tailed left-tailed test, that is, if we wish to find evidence to suggest that mu1 is less than mu2, our null is mu1 is greater than or equal to mu2, or that mu-d is greater than or equal to 0, and the alternative is that mu1 is less than mu2, or that mu-d is less than 0. The critical value will be negative, and we reject if the test statistic is less than the critical value. Or for a p-value approach, the p-value will be the area to the left of the value of the test statistic, and we reject if the p-value is less than alpha. For this type of test, if we reject the null, we conclude there is evidence to suggest mu1 is less than or equal to mu2.